There's a word, a subject, a topic of interest that I think people don't know as much about as they should.
Okay.
It's all about isotopes. You remember the periodic table of elements, that mysterious chart of boxes that hung in the front of the room all year in chemistry class?
Yes.
There's a sequence of elements beginning with hydrogen, and they get sort of heavier and heavier and heavier.
Right.
And they each have a number. So hydrogen is number 1, helium is number 2. So we're not just numbering them, that is the count of protons in their nucleus.
Right.
Who's got 12 protons? Who's got 6 protons? There is an element, and only one element that has that many protons in the nucleus.
There you go.
Some famous ones, carbon has 6 protons.
6 protons.
Oxygen has 8 protons. I left one out. Nitrogen has 7 protons.
Okay.
Uranium has 92 protons.
Okay.
When the periodic table of elements was being discovered, there were gaps. So you knew exactly what to look for if you were missing an element. Look for the one with 39 protons. Go back to the lab.
It's like a chemical Lego set.
You just put it in a slot,
Click.
clicks right in, and you move on. And so we have found 92, quote, natural elements in the universe, 1 through 92. Hydrogen right on up through uranium. And we have another, how many? Up to 118 now, going beyond uranium. We made those in the laboratory.
You think you can play God, sir? Is that so? You're just making elements now?
The answer is, frankly, yes.
Yeah, there you go.
So these are the protons, and they're immutable. What I mean is, if you take away a proton, it's no longer that element, it's the other element.
Right.
If you add a proton, it's now a different element. Wait a minute. Protons all have the same charge. They all have positive charge. So what does it mean to cram them into the nucleus of an atom if left to their own devices, they would what?
Oh man, they'd be the Real Housewives of New Jersey. That's what they'd be. Get out of it! Get out of it! What you? Flip the table!
So what holds them together? Well, there's a whole other force of nature called the strong force.
Fundamental force of nature.
Fundamental force of nature, and it's propagated by a particle called the gluon.
Right.
Aptly named, I might add. And this happens by the presence of neutrons in the nucleus.
Right.
So neutrons tamp down the resistive forces, and they act as a sort of a glue for the nucleus.
Unless you're a Martha Stewart atom, in which case it's a hot gluon. That was terrible.
They all can't be winners, like you said.
Exactly. I'm going to tell you, Martha should not have gone to prison for that. I should have.
So hydrogen in its native state only has 1 proton.
Right.
It doesn't need a neutron.
Right.
To hold anything together. So native hydrogen is just 1 proton and then 1 electron on the outer side. Oh, by the way, in a red-blooded atom, they have as many electrons as protons. So they're electrically neutral.
Right.
Okay? So uranium would have how many electrons?
As many as it has neutrons.
No, as many as it has protons.
I mean protons.
Protons. So how many is that?
I don't know.
You don't remember? I said it.
92.
92, exactly. 92. So matter is generally neutral for this reason. Okay, hydrogen is happy. Let's go to helium.
Right.
Helium has 2 protons.
Right.
Its native state has 2 neutrons.
Okay.
Suppose I force hydrogen to accept a neutron, and I cram it in there, okay? I can do that. Now I have what's called heavy hydrogen.
Heavy hydrogen.
It has a whole word that we have for it. It's called deuterium.
Oh.
You might have heard the word deuterium.
Do tell, what does deuterium do?
You can make a water molecule out of deuterium. H2O, if one of those hydrogens is a deuterium, then it's DHO.
Is that heavy water?
That's heavy water.
Heavy water?
You might have heard of heavy water, yeah. You can add 2 neutrons to it.
Okay.
We have a word for that.
Obese water.
It's called tritium.
tritium.
Point is, when you do this to an atom, adding neutrons or possibly subtracting neutrons, if it has stuff it won't miss, you made an isotope.
Aha.
So deuterium and tritium are isotopes of hydrogen.
Of hydrogen.
Let's go to carbon. Carbon has 6 protons in the nucleus.
Right.
So red-blooded carbon would have how many neutrons?
6.
6. And it'll have 6 electrons.
Electrons.
Carbon.
There you go.
Bada bing.
There it
Okay?
is.
Oh, wait a minute. I can add 2 neutrons to it.
Ooh.
So now it has 6 protons and now 8 neutrons. Add those 2 numbers to get. What do you get?
14.
14.
Carbon 14.
Carbon 14.
As in carbon 14 dating.
Yes. Yes. You know, someone should make a carbon 14 app, a dating app. That'd be kind of cool. That'd be kind of cool. So that's an isotope of carbon. All right. It turns out carbon 12 is stable. 12 is 6 protons, 6 neutrons. It's stable.
Right.
You add 2 neutrons, it's not stable.
Right.
It will decay
In a half-life.
in a half-life. And the half-life of carbon 14, if I remember correctly, it's around 5,000 years, which means after that amount of time, half of the carbon 14 is no longer there.
Right.
It has decayed. And then you wait another 5,700 years, half is gone again.
Right.
You wait another 5,700, it's half of a half is an eighth.
Right.
So you keep doing this, and you know what it does? It gives you access to dates across all of recent human history. From when we were in caves, up through recorded history, right on up back through 1,000 years ago, 500 years ago. So it's very useful for dating life on Earth. Some carbon that's in your body is carbon 14.
So how do we end up with the carbon 14 in our bodies?
So carbon in nature, add carbon 13 in there too. So carbon 12, stable. Carbon 13, stable. There's not much of that. Carbon 14, unstable.
Unstable.
Okay, so in the environment, carbon 14 would normally just disappear, except there are sources of carbon 14 from cosmic rays from space.
Space rays?
Space rays!
Space rays.
Space rays.
We got space rays.
Okay, you know what else boosted carbon 14 levels?
What?
The nuclear tests that went on in the 1950s and 60s.
Ah.
So here's what happens. When you are alive, you uptake that native amount of carbon 12, 13, and 14 into your body.
Okay.
And it stays at that level, okay, until you die, because then you stop ingesting more carbon. There's carbon in all food you eat, basically.
Right.
All food that has any nutritional value has carbon in it, okay? The moment you die, you're no longer refreshing the carbon. And the carbon 14 then decays.
And then that's when we can figure out the timing.
Correct. The nuclear tests have interfered with some of the baseline measurements of what's going on in our environment. So you have to sort of get the nuclear tables together with the tables of nature in order to figure out what the starting levels were for life forms that were exposed to it.
We've actually put the finger on the scale.
The thumb on the scale.
The thumb
Yeah,
on the scale with the nuclear test.
yeah, with the nuclear test. Anyhow, I was just, chewing the fat here with isotopes.
I love it.
And, they're fun other part of what's going on the periodic table of elements.
Yes.
And one other thing, hydrogen has 1 proton and helium, remember, has
2.
And helium in its native state has a total of 4 nucleons, 2 protons, 2 neutrons.
Right.
And it's stable. Okay. It turns out that's called helium-4 because it's got 4 particles in its nucleus, 2 protons, 2 neutrons. Helium-4. If you take away one of the neutrons,
Right.
guess what you have?
Helium-3?
Yes. Helium-3.
Helium-3.
Now, here's what's cool about helium-3. Helium-3 is one of the particles ejected by the sun.
Right.
And it gets embedded into the lunar surface. We might have talked about this in another show. So helium-3 is yet another isotope, but now that's one with 1 fewer neutrons instead of more neutrons than what was there before.
Nice.
All